Why does all of this matter? It matters because of our oil return and our ability to carry the load of the refrigerant. So if we don't size this properly, one, we're not going to get the proper BTU flow through the refrigerant stream, which means the system is not going to be able to keep up. We're going to have problems at the compressors and at the evaporators with them controlling load properly. And then two, we're not going to get the oil return that we need, which is where these traps become very, very critical. What we're working with is we have an air handler on a roof that is serving a multi-story building in a downtown space. So this air handler has a vane axial fan assembly that is running all the supply air, and our refrigerated coils are right here. Now we've actually got two condensers. They're split system carrier, they're 80 tons, that currently serve these coils. We're replacing those condensers and putting in new York YULA 95 ton condensers in their place. That was an option that the customer requested. They wanted their total system design allowed for the little bit of extra tonnage, so they went for it and chose it. So the scope of this job is we're coming in, we're moving these coils here, and this is actually two banks. You have one bank here and one bank here on an angle, and these two banks are what serve the supply air for this air handler running multiple floors. The condensing units are over here to the side outside of the penthouse where this air handler lives. Typically in a situation like this, we bring the manufacturer in, we walk it with their design engineers, we go through this whole process. Jobs like these take, a year, 2 years to put together, bid, go through, get approved, order. A lot has to happen to make these kind of jobs happen. When we got to the site and began to really look at, okay, how did we need to finalize the piping schematics so that we knew exactly how to go back with this and what we were going to do, we could not get a solid answer from York as to what they wanted us to do. Specifically for this exact application, could we reuse the old line set? Could we get the new line set? They wanted new systems, one, because they had really old carrier condensers, and they wanted something more efficient with better loading abilities and that had a newer refrigerant. So all of these are R22, and they wanted a 410A system. The old carriers are semi-hermetic Carlisle compressors, and we had 2 circuits per condenser, 1 compressor each circuit, whereas the new system is 2 circuits, 3 scroll compressors per circuit. So we have a lot more loading and unloading capacity in our ability to really fine tune it. And one of the struggles they had is during the low load times, they were constantly having issues not having to short cycle the carrier condensers because they couldn't quite match the load the way they really needed to. And keep in mind, there's an automation system that makes this whole entire puzzle function. The condensers have some onboard controls that are mostly built there for safety purposes, but for the most part, a building automation is actually what is controlling the brain for this entire setup. To kind of give you an idea of how the original was set up was here at each bank you had a set of stacked coils, and this was times 2, and I'll get into what I mean by that, but each circuit had a liquid line that come out, and then it would hit this little header assembly, and they went through 2 solenoid valves and then went into each TXV, and then the suction lines came out, had a trap, and then hit a header that come up and come all the way back to the condenser. They ran 1 1/8" liquid line and a 2 1/8" suction line for this on this R22 system. This was times 2 for the other circuit. So you had another set of liquid and suction line come out and did this exact same thing, and kind of a depiction here of it is each TXV, you've got the distributor tubes that kind of split the entrance of the coil, and what that means is this entire coil, both coils in this instance are actually having refrigerant flow the entire time. They are So we are processing all of the air moving through this coil at any given time, and it would be the case for both sets of coil banks. And you see the suction headers come out the other end of the coil and flow through. I have another diagram in here I will show you. So on this diagram, and what's funny is that actually this is all York data, by the way. They actually state that their recommended setup is a 2-circuit coils stacked, when you do a stacked coil system like this. So your circuit 1 would have TXV 1 and 2, circuit 2 would have TXV 3 and 4, and those would serve in a stacked coil instance. And they actually even specifically say in 2-circuit or in a stacked coil scenario not to do individual circuits. You know what's funny? York designed this to be exactly this way, against their own specific recommendation. That is how the current system is set up that is in place. What that left us in is now we're in a position to where we've got a completely different setup. We've got a situation where we've got a stacked coils, and they're expecting us to serve one coil per condensing unit. Now, when we first got all this paperwork and got the design based off of their own paperwork, which we are level, so this unit is designed to where the evaporator could be, you know, several stories above the condenser, could be several stories below, or it could be even at the same level or same story as the condenser itself. It's just traveling across a horizontal face instead of having any kind of vertical run. Per their own setup, like this was how they were depicting they wanted us to hook it up. The problem is we've got a 2-circuit machine, and that's not the way. This is not what they sent us when they gave us all the material, the coils. This isn't what it looked like. It didn't look like any of this, because here you've basically got one main liquid line coming in, splitting between the coils, which, going back to their schematic, this is what they recommend. They want you to have a split header so you get all the surface area covered, and then you would have one main suction riser coming back up and out, going back to the condenser. You can also have a hot gas option. I'll talk about that more a little bit later. We do not need that with our current setup. One of the things I do want to point out as I'm going through this is the design principles for you guys who are still in school, maybe looking to go to school, getting ready to. There's going to be things that they cover in there in terms of oil return and velocities and proper piping design if you go to a really good program. I know there's programs out there that don't even bring that stuff up. But if you do, don't brush over that information, because I remember doing this stuff when I was in school, and jobs like these are where it came to really benefit me. So what that led us to is, okay, are we actually supposed to have a split coil setup, or were we supposed to have a dedicated coil, meaning each coil was going to be dedicated to a single circuit? Because if we're looking here, we have one set of liquid and suction line coming out and another set for this circuit. So here's your 2 circuits. If we're supposed to run these together, this machine was not designed for circuit 1 and circuit 2 to all of a sudden become one big tandem circuit. That was going to cause a lot of problems and complications. And honestly, ultimately, it doesn't make a whole lot of sense that they would have us do it that way. Between the fan cycling controls and the compressor controls, and then the velocity issues we were going to have because we had such big pipe at that point, it just did not make sense that we could have reasonably needed to tie the 2 circuits together the way it was being depicted. What this is leading to is York is contradicting themselves to how they actually designed the system versus what their recommendations on system design is. Eventually we came to the understanding that we were going to need to do a dedicated coil per circuit. That was the simplest thing, which meant that this header assembly went away, this whole setup went away, and that was no longer going to be the case. We weren't going to have this, because the coils we received were single circuit coils. Actually, just like the ones depicted here. These are single circuit coils. This would be considered a dual circuit coil. So we got these coils in to replace the existing coils, which meant that our overall design did change when they sent us this equipment. Now that has other ramifications that I'll get into later about how the automation system is going to be able to control that, and we'll discuss that in a bit. But then we had to decide, okay, is the existing piping going to be sufficient? Can it stay? Do we have to replace it? And keep in mind, we're talking about, replacing almost 100 feet per circuit worth of copper. You're talking 4 circuits total. We're talking tens of thousands of dollars worth of copper and manpower to do that. That's a major expense to go onto the project. Obviously, with a 410A conversion, we will need to do a flush on the line set if we decide to keep it. So with us settling on, okay, York intended us to have dedicated coils. I know everything in this book tells us that they never want that to be done, but ultimately that is exactly what they sent us. We have 50-ton circuits on this machine, and those circuits are able to go from that nominal 50 tons to a little over 17 tons. These TXVs being 50-ton valves, they're the OVE 50s. They have an ability to derate themselves down to 13% of total capacity, meaning that if you do the math on that, so that is 50 multiplied by 0.3, takes you down to 15. So we can do as little as 15 tons of refrigerant volume through these valves and still be able to maintain superheat control on the suction line. So that matched up perfectly. Now we're entering a stage of, okay, what lines do we actually have? Like I said, on average, you've got just shy of 100 feet of actual line set length. I'll use one unit for an example. Has an actual length of, we'll use the liquid line, of 60 feet total. Now, there's some things and some design parameters you have to take into account when you start looking at this. So that's 60 feet from the unit to that coil and where we're tapping on that TXV. We have to calculate the physical length and each of these turns. Each 90 and T, every one of those joints creates a restriction in the system. So we have to calculate that into our overall total footage, which I have a chart here. This chart does exactly that. So we're able to go, and so we know that this is in OD sizing. So 1 inch is our 1 1/8 inch. So we know that for every standard 90 installed at 1 inch on the liquid line is equivalent to 2.5 feet of actual line length. That's the amount of restriction that it creates. If you use a long radius, you're able to cut that down to just shy of 2 feet. So as we roll through this, these are the additional calculations we're having to factor in. So over here, that actual 60 feet that is the physical length measured, you calculate the joints that we have to create to get from here to here, you end up with actually just right at 100 feet, which fortunately for us is right at design specifications. Per their ratings, they will allow 100 effective feet or 150 calculated feet based off of their piping designs and the information they sent us on this equipment. They quite literally sent us 5 different submittals for this equipment and coils, which totaled out to be about 300 something pages worth of documentation. I was able to sort through that because that was blended between 410A, 407C conversions, and R22 systems, and I got a little under 100 pages worth of relevant data to just the 410A side, which is what I was focused on, and I've been able to extrapolate everything I need from there. We know that we're pushing the limit, and I do mean pushing the limit on the line length, with it being 1 1/8 inch. So the existing system is 1 1/8 inch on the liquid, 2 1/8 inch on the suction. There's some things that we have to keep in mind as we're going through this. One big thing that really stands out is they want us to only use 1 liquid line solenoid per circuit. With the way they originally had it, they had 2 solenoid valves per circuit. It was 1 per TXV. We will quite literally look exactly like this going into our system, where we're coming out the liquid line and we'll come down and tie into each coil. So this would be like circuit 2's coil and circuit 1's coil. To factor that, we really need to know what line sizes we need. York has some very specific design parameters for when we're doing the calculations for the liquid line. We are not to exceed design parameters for 1 degree of temperature loss on that line. That's going to play into what size of pipe we're allowed to choose based off of that parameter. At the same time, the suction line, we're not allowed to gain 2 degrees of that loss. Those are very critical design parameters because you can have some different numbers there, but for this system to function properly, that is what York is calling for. Now we have to stay within that. A couple other things we have to take into consideration is they want to have P-traps on the outer outlet of the evaporators, and then if we have actual suction risers, we have to have inverted traps. We do not have a true suction riser. Even with doing the system setup that we have here, this is not considered a true riser. It's all one level on the same floor. And you can even see they don't even depict having a suction riser there. But there is a primary P-trap. Now I'm not having this extra loop here that you see depicted. We don't need that for our particular setup. York does give us this diagram, and our design spec was designed for 45 degrees of suction saturation. That's at a 2 degree loss. And if we go up to 2 1/8, which is what we currently have, we're allowed 56 tons total of volume through that pipe. I do want to point something out here. You see that? That was a typo made by the manufacturer. That's supposed to say 2 5/8 and then 3 1/8. Be careful, guys. Be very, very careful. Something like this will mess you up bad. So just pay attention to what it says. 56 tons is okay. Now, I said earlier we have a 95 ton unit, but each circuit is a nominal 50 tons. So 56 tons covers our current conditions, and this is at that 100 feet worth of line. They have this diagram, but they also provide this chart, and this chart is very similar, but it is different. And you see up here at 40 degrees of saturation at 1 degree loss, and this is for suction line, we would end up with to get our size, which up here this is rating at 61, that's going to bring us across to 2 5/8. Now what this means is if we were designing, or if we had designed for a 40 degree saturation, we would have to be stepping up to a 2 5/8 suction line to support the tonnage of this system. But because it wasn't 40 degrees at a 1 degree loss, which adds a lot of volume requirement, we were only at 45 degrees with a 2 degree. That made it possible for this 56 at a 2 1/8 suction line to actually work. It's just enough, but per their own parameters, they say it will work. Now, we obviously are definitely going to have a trap, and I'll show you my schematic I drew here earlier. We're having suction traps right here coming out of the coils. That is a given. Why does all of this matter? It matters because of our oil return and our ability to carry the load of the refrigerant. So if we don't size this properly, one, we're not going to get the proper BTU flow through the refrigerant stream, which means the system is not going to be able to keep up. We're going to have problems at the compressors and at the evaporators with them controlling load properly. And then two, we're not going to get the oil return that we need, which is where these traps become very, very critical. If you're spanning floors and you have a true suction riser, you have to look at having traps. And if you're spanning multiple floors, you have to look at installing traps in between the floors just for your oil management system. Guys, I've worked on systems that they didn't do that, and they went 3 to 4 floors and had no risers in between, and it's not going to function. They're always going to be buying compressors. We were able to reuse the 2 1/8 suction line and just repipe it in on that single coil. The next question becomes, okay, what about the liquid line? Thankfully, the liquid line doesn't have quite as many heavy parameters as the suction does, but it is still important because we have to maintain proper velocity and volume. Now, looking at that, we have a different chart for the liquid line size, and with a 1 degree drop allowance, we come down to our tonnages, and right there, so we're showing 45 tons for 1 1/8 inch. What that means is we could not be any closer at pushing our design limit for that 1 1/8 inch. Now, we've got a little bit of wiggle room, and these are not extremely exact numbers. And it's not actually, like I said, it's a nominal 50 tons, so it's actually 40 something, right at that 45 mark. So if we were an extra 15-20 foot longer on our pipe length, we would have to be upsizing our pipe here. Thankfully, we do have just enough room to make this work. What about the hot gas bypass? Now, they did not send us coils with the distributors having a hot gas bypass circuit attached to them. And you can see that depicted here. Right there, that is a special adapter that goes onto those distributors for that purpose. That adapter is not there on the coils they sent. And looking into it, the hot gas bypass is ultimately there to help assist with lower load conditions so that you can maintain proper coil saturation and temperature at less capacity. So reading through their specifications, they actually spec that if you were to need and use hot gas bypass, you could get down as low as 5 tons on this system. At the end of the day, though, we do not actually need that. So that ultimately leads us to our final design we will have. We're no longer going to have these split lines with the headers where our liquid lines are going to 2 valves and so forth. Each circuit is going to come across and tap into 1 TXV, and you're going to have 1 suction with 1 trap. And per their specifications, we're going to be able to come out of each of these coils, process through our trap on the suction, and make it back to the compressor, and then come back in with 1 solenoid valve hitting that single TXV, and we'll be perfectly fine with that. This system actually gives us a lot more flexibility once we get it set up properly, because since we'll have 3 scroll compressors, our ability to match load conditions will be much greater than before. Now let's come back to the main air handler. There is some drawbacks we have to keep in mind. When you're running the system like this, if circuit 2 is off and circuit 1 is the only one running, that means that all the air processing through that other coil is not doing anything. You have to take some very specific design parameters and configuration parameters into account when you do this. And this is where we had to have a very in-depth plan with our automation side that controls the system. At any point, this system was going to have to be configured so that it ran a balanced load across the circuits. It could not do an actual lead lag setup. So a lead lag would do your circuit 1, compressor 1 and 2 and 3 would stage up and get fully loaded, and then it would look at bringing on circuit 2 if required. With a balanced load configuration, we'll cycle 1 compressor per circuit at a time. So stage 1 would be C1 compressor. Stage 2 would be circuit 2 compressor 1. And then back and forth, it would hopscotch on the staging up of the circuits. And what that will do, if our 2 lowest stages is one compressor per coil, then that will make sure that we're processing all the way through. Now, there are real conditions, and we've ran into this before, where during our mild times of the year, where we run between like 70 to 60 degrees outside, it's not cool enough to actually run free cooling. So we still need mechanical cooling, but it doesn't take a whole lot for the circuits to satisfy a 55 degree supply air. It's just such a little load. But we have a ton of humidity even at that point. We have very saturated conditions in our area, not to mention all the humidity stacking up in the building. What a setup like this will cause, if we didn't do it properly, is we're going to lose control of the humidity in the building, which is going to create a lot of condensation issues and make it just very uncomfortable for the tenants. We have to make sure that we are staging the circuits properly, but then our automation team is also looking at coming in and installing louvers on each of the coils. And what they'll end up doing is they'll build a logic program that works with the supply fan commands, so that if we only need circuit 1, compressor 1 to maintain supply air on that condenser, it will close a set of louvers and stop flow through the additional coil, so that we're only moving air through this coil. Now, granted, you're talking about a time where we have a really low load. What that's going to do is that's going to process all of our air that we need to process through that single coil, and it's going to make sure that we're not allowing too much humidity to stack without it being processed at all in the space. And if we do that on both sides of the system, it's really going to help protect the building from having those types of high humidity issues or anything of that nature that's going to cause a lot of discomfort. This is not a fix for everything. This was a very specific look at a very specific situation. My overall goal and what I was trying to point out was, one, I wanted to give you a picture of some of the stuff we can get into. This is not something an everyday technician would do. So this is just one area that you can get into to really kind of expand yourself in your career, and this, in my opinion, can be really neat. Now, it takes hours of sitting down, reading through, getting very specific, and even making very specific notes. Like, there is a exact procedure that they want you to follow to set up this trap. Ultimately, you have to stick to the manufacturer's guidelines, because if you go outside of their design guidelines in any significant way, it makes a really easy case for them to come in when they have to start issuing warranty problems because of design issues, where they go, well, you didn't do this properly, you didn't set this trap up right, or you didn't do this, you didn't do that, and so because you didn't do that properly and you have no documentation to prove that we told you could do that, you now own this, the warranty is void and it's yours, right? That's the kind of stuff that we can get into and what you have to be really careful of. So it takes a lot of time to really go through this. This is not an exhaustive how to build out every large commercial system out there in piping design or anything of that nature. But I did want to share this experience. This is not something I get to do all the time, but when I do have it come across my desk, I do really kind of have fun playing with it every now and then. Hope you enjoyed it, guys. Love some feedback on this entire setup and process and your experience and what you've ran into. Leave it in the comments. I'll see you on the next one. MTT, take care of your family, take care of your spouse,